मैं डॉक्टर अशोक सैनी, एसोसिएट प्रोफेसर मैथमेटिक्स, BLJS कॉलेज तोशाम, today I will deliver a lecture on programming in C and numerical methods of class BA BSc second year semester 4th, and the topic of this lecture is we have done previously Descartes' rule of sign to find a root of an equation. Now we will discuss we have given this Descartes' rule of sign in the previous lecture in a polynomial equation fx equal to 0 with real coefficients. The number of positive roots cannot exceed the number of change of sign for variations of the coefficients in fx. The number of negative roots cannot exceed the number of change of sign for variations of coefficients in f of minus x. We have done the proof in earlier lecture. This is the proof of this theorem, and then we have location of roots. We have given this lecture also, and for the proof of this theorem we have P and P1, and this is another P and R. The root lies on x-axis where the curve cut the x-axis at x equal to c, x equal to c1, x equal to c2, and if the curve not cut x-axis, then there is no root of the equation, and if it cut, then it has even roots. Now we will go from this ahead. Theorem: every polynomial equation of an even degree whose last term is negative and coefficient of first term being positive has at least two real roots, one positive and other negative. Proof: let us consider the equation fx equal to a naught x की power 2n plus a1 x की power 2n minus 1 plus so on minus a 2n equal 0. This is the equation of minus infinity to plus infinity x-axis, and this is y-axis. Now putting x is equal to infinity, and in this we will find the value is also infinite, and when we put x equal to 0, you will see all the terms cancel, only constant term remains minus a to n. Here f of infinity equal to infinity and f of 0 equal to minus a to n, and f of minus infinity, we put minus infinity, it still comes out with plus infinity. Now from this we find that as x approaches from 0 to infinity, fx changes sign from negative to positive. Therefore the equation fx equal to 0 has at least one positive root in 0 infinity, and when x approaches from minus infinity to 0, fx changes sign from positive to negative. Hence f of x equal to 0 has at least one negative root in minus infinity to 0. Next theorem is every polynomial equation of an odd degree must have at least one root, a real root of the sign opposite to that of its last term, the coefficient of the first term being positive. Prof. Let us consider the equation fx equal to a naught x की power 2n plus 1 plus a 1 x की power 2n plus so on plus a 2n plus 1 equal to 0. Here f of minus infinity equal to minus infinity, f of 0 equal to a 2n plus 1 and f of infinity equal to infinity. If a 2n plus 1, this a 2n plus 1 last term is positive, fx change sign from negative to 0, from negative to positive in the interval minus infinity to 0, and therefore the equation fx equal to 0 has, when there is a change of sign, there is a root. Fx equal to 0 has at least one negative root. If a2n plus 1 is negative, fx changes sign from negative to positive in the interval 0 to infinity, and hence the equation fx equal to 0 has at least one positive root. Example 1, show that the equation x की 5 minus 5x plus 2 equal to 0 has 3 real roots. Find the interval in which they lie. Solution: let fx equal to x की power 5 minus 5x plus 2, which is given, and when we put x with negative x, then this becomes minus x की 5 plus 5x plus 2. The number of variations of signs in fx is 2 and in f of minus x is 1. Therefore, there are at most 2 positive and 1 negative root, positive or negative signs of fx at x equal to minus 2, minus 1, 0, 1, 2 are as follows: x sign of fx minus 2, minus 1, 0, 1, 2. When we put in this x minus 2, fx sign of fx minus, when put minus 1, sign of fx is plus, when we put 0, sign of fx is plus, when we put x equal to 1, sign of fx is minus, when we put x equal to 2, sign of this is plus. Then this shows that there are exactly 3 real roots, and the interval in which they lie are minus 2 to minus 1, because there is a change of sign, minus 2 plus 0 to 1, 0 to 1, minus to 0, there is a continuation of sign, and 1 to 2, minus 2 plus. When there is a change of sign, there is a root. Next, example 2, show that one of the root of the equations lie in the interval indicated against each equation. X square equal to cos x 0 to 1 and x square equal to log of x to the base e plus 4 2, 3 in the interval 2, 3. Solution: let fx equal to, given is x square minus cos 2x, and f of 0 is equal to 0 minus 1 is equal to minus 1 negative, f of 1 is equal to 1 minus 0.5402. We put 1 in this expression, x square equal to cos x. Cos 1 is from table, 1 radian is 57 degree 18 minutes, and cos 57 degree at 18 minutes is equal to 0.5402 from cosine tables. When f of 0 we put in this fx is negative, when we put f of 1 this is positive. There is therefore the change of sign. Therefore root of fx equal to 0 lies in 0 to 1. Next, second part, given is fx equal to x square minus log x to the base e minus 4. We put when f of 2 to 3, we have to find in second part 2 to 3. Put f of 2 4 minus log 2 to the base e minus 4, and putting the value of log 2, we find this is negative, and f of 3 is equal to 9 minus log 3 to the base e minus 4 is equal to 9 minus 1.0986 minus 4, which is positive. Root of fx equal to 0 lies in the interval 2 3. Example third, show that the equation x cube minus 4x square plus 7x minus 5 equal to 0 has at least one positive root and the interval in which it lies. Solution: degree of equation fx is equal to x cube minus 4x square plus 7x minus 5 equal to 0 is odd, and last term is negative. Hence the equation fx equal to 0 has at least one positive root by theorem 1.5.3. Also f of 1 is equal to minus 1 and f of 2 is equal to plus 1. So there is a change of sign, minus to plus. Since here fx changes sign from minus to plus as x approaches from minus plus 1 to 2. Hence the positive root lies in the interval 1 to 2. Now in the next section we will discuss solution of algebraic and transcendental equations. In the previous section we have discussed the nature and location of the roots of the equation. Here we shall describe some numerical method for the solution of equation of the form f of x equal to 0, where fx is algebraic or transcendental or a combination of both. Bolzano or bisection method. This method is based on the result that if a function fx is continuous between a and b, and f of a and f of b are of opposite sign, then there exists at least one root between a and b. For definiteness, let f of a be positive and f of b be negative, so that root lies between a and b, and let its approximate value be given by c equal to a plus b by 2. Now 1. If f of c equal to 0, then c is the root of the equation fx equal to 0. Second case, if f of c is not equal to 0, then the root lies either in a to c or c to b, depending on whether f of c is negative or positive. We again bisect the interval and repeat the process until the root is obtained of desired accuracy. The example illustrates this result. Example 4. Find the root of the equation x cube minus x square minus x minus 3 equal to 0 by bisection method. Correct up to 3 decimal places. 3 places of decimals. Let fx equal to x cube minus x square minus x minus 3, since f of 2 equal to minus 1, which is negative, and f of 3 is 12, which is positive. Therefore root of the equation fx equal to 0 lies in the interval 2 to 3. Bisect this interval by point 2 plus 3 by 2 equal to 2.5 in the interval 2, say 2.5 and 2.5 to 3. Polynomial equations are called algebraic equations. Now since f of 2.25 is positive, therefore root lies in the interval 2 to 2.25. Again bisect this interval to obtain the interval containing the root, repeating the procedure again and again, we get the root up to the desired accuracy of degree. In tabular form, the process may be carried out as under A, f value of f a, b value of b, a plus b by 2. First we take 2, this is negative, f of a is negative 3, when we take 3, f of b is positive, and a plus b by 2 is 2.5, and f of a plus b by 2 in this expression is positive. Continue this process. 2 is negative, 2.5 is positive, and 2.25, 2 plus 2.25 we will find out, it comes out to 2.25. again f of 2.25 is positive, so negative to positive, therefore root lies between 2 and 2.25. we put 2 negative, then we put 2 negative, 2.25 positive, again taking of mean of these 2.125, this is negative. 2.125, the value is negative, we will shift the 2.25 positive, again we taking mean 2.187 positive, and continue this process. We will find this sign. From the above table, it is clear that the root lies in the interval 2.130 and 2.1306. Therefore, required root correct to 3 places of decimal is 2.130. Students, today we have studied Descartes' rule of sign, examples, and bisection method and its examples, and you will see this lecture on our college website www.bljscollege.com YouTube channel. Thank you very much. Thank you.